Welcome back to our statistics learning session. Today, we'll be talking about a test based on log likelihood. If you remember, in our previous exercise, our test was based on x-axis. That is, we had we had something like this, where this was an axis, and there's a Gaussian that is based on this x-axis, and there's another Gaussian that is based on this x-axis, and these are x1 and x2. Those were x-axis I'm talking about. Now, what we are trying to do is not only we take x-axis, we're trying to do a test based upon y-axis also. What I mean is, our theta was based on x-axis on previous test, but in this test, the theta is in x-axis, and we are trying to do a test based upon the y-axis. So if I want to visualize this, then it's going to be something like this, where this is a maximum likelihood, which is fair or not, and we have an estimator, which is MLE. We have a theta, we have we have a theta, which is maximum likelihood estimator, and this is fair or not. And if you look at a y-axis, what we are saying is that the difference between y that is related to theta MLE and y that is related to theta naught, theta MLE and y theta naught should be really small, really small. That's what we are saying here. And that's what we want to prove. Now, let's begin. We know that theta MLE is a maximum likelihood estimator. And by definition, the maximum likelihood estimator is a function, random variable that fluctuates. It has some fluctuation. Okay, it has some fluctuations. Some of it is here, some of it is here. It just fluctuates around theta milli, theta naught. And what we are trying to say is that this fluctuation is just really small. For this test, we have general setup where we have x1 through xn is just some random variable with a statistical model, a sample space E, and probability distribution in the theta naught, where theta naught is a random variable in d dimension. For this one, what we are trying to do is for null hypothesis, we are saying that we have a variable r. It can be 0, 1, 2, anything, but all the coordinates after r are same between theta and theta naught. Now assume that theta naught on theta is a multivariable Gaussian, or it has a many variables. Okay, can we assume this? Yes, we can. Let be a multivariable, not only a single variable, but it's a multivariable, and it has a many coordinates. Theta and theta have many coordinates. That is, it is theta, then it has theta naught, theta 1, theta 2, right? And theta naught would have something like this: theta naught, theta 1, theta 2. It was something like this. It has many coordinates, and what we're saying is after a certain number r, let it be, let's say r is 0, then theta naught, theta 0 through theta 2 for theta is same for theta 0 through theta 2 for theta naught. It should be same. That's what you are saying. And what if it's a single dimension? If it's single dimension, then theta is equal to theta naught, because it is not a it is not a it is not a vector, or it doesn't have any many coordinate. It is a one single coordinate, so it's going to be just theta is equal to theta naught in that case. So what we are saying now, what have we discussed till yet? We have said that in past the theta, we did some test whether theta naught is equal to theta mle, and that was based on x-axis of Gaussian. Now what we are saying is that we will test whether theta naught is equal to theta mle, not based on x-axis but based upon the y-axis. And for that, we have a general setup where we have some x is random variable, which is with a dimension d equal to 1 or greater, and we have a null hypothesis where we have picked out a random a variable r, which can be 0 or more, and we are saying that for all the variables after r, or all the coordinates after r, has to be equal between theta and theta naught. That's all we are saying. So that's all for today. I'll see you next learning session. Thank you so much.